Hi, I'm Josh. I'm from Los Alamos National Laboratory. Let's build a Rayleigh waveform detector. So Rayleigh waveforms are surface waves with often retrograde and elliptically polarized particle motion. This motion is confined to a vertically oriented plane that contains both the source and receiver, which is called the sagittal plane. The waveform characteristics in this plane are determined by the source, the site of the source, the waveform dispersion at this site, and the sensor. But importantly, the waveform motion remains elliptically polarized in that sagittal plane regardless of what the source and particular site are. So we will use this signal feature in particular to build a waveform detector from the ground up. So we thereby present two competing models for our seismograms in this green sliding window that you see in the data. Under the null hypothesis, we assume that all three components of the motion contain only noise. And under the alternative hypothesis, the data are a sum of signal and noise. We do not know the azimuth of the source for the signal. In other words, we don't know what the orientation of the sagittal plane is ahead of time. So the data models, however, become more specific when we record Rayleigh waves. In this case, we replace the models for all channels with just a model for the vertical channel. We then phase advance this vertical channel by 90 degrees with a tool called the Hilbert transform that many of you are probably familiar with. We then model the radial motion to be linearly correlated with that Hilbert transform vertical channel I just talked about. And because you nor I know the source location ahead of time, unless we're clairvoyant, we explain this radial motion as an unknown rotation of the east and north channels to that sagittal plane. So next we form a generalized likelihood ratio. And this is really where we retrieve the detection statistic. And what this ratio is, it is a quotient of the two densities for our data models. We populate both of those densities with maximum likelihood estimates of the unknown parameters in the data that include the noise variance and the unknown azimuthal angle, which we're calling theta, of the sagittal plane. The quotient forms the detection statistic. It projects energy in the phase-advanced vertical channel onto the subspace spanned by the motion in the horizontal plane. It compares this energy in this projection to the energy that's left over in the original data. If this statistic then locally exceeds a threshold, we declare a Rayleigh waveform is present in the data, in that green window you saw earlier. If the threshold instead locally exceeds the statistic, we declare that we've only recorded noise. And I want to correct something I said. I earlier said that theta is the azimuth. Rather, it is the back azimuth is the arctangent, I should say the four-quadrant arctangent of the components of theta, which I've shown in this equation below. Sorry for that correction. So now with this detector defined, we can wrap it into a module with lots of subroutines that will allow us to apply it to three-channel data autonomously. So the resulting module has that I've described, which I'm yet to describe, has various capabilities. In the simplest case, we can apply this module against seismograms in a single frequency bands and update thresholds and other estimates once per full seismogram. In the more sophisticated case, the module is more like the scan function in an old AM/FM radio in a car. It processes the data in multiple sub-octave frequency bands and updates the threshold and many other parameters regularly with Bayesian estimators. I will focus running the detector in this Bayes mode for both the single and multiple bands, but I should point out that we also have these other capabilities in these simpler cases. So now I will make this demonstration against near-surface explosions that are recorded at local distances with just one sensor. And so we will thereby collect waveform data sourced by Russia's invasion of Ukraine and cataloged by Dando and others in 2023. Here, the larger circles mark larger explosions that were captured between the summer and winter of 2022. And I thank Jonas Kintner for the map. We exclusively use data here at station AKBB within the Malin array, and will focus on two particular event sequences, which I have outlined in blue and red. The first event we detail contains many overlapping RG signals, and we'd like to initially confirm with this first example that we can detect these events and localize their sources at least azimuthally. So that's what we'll start with. And we do detect them. The top seismogram shows a 2-hour record that includes a series of explosions. The squares here mark Rayleigh waveform detections, or what we're perceiving to be Rayleigh waveform detections. The bottom plot shows the scalar detection statistic on a vertical log scale. The red line shows thresholds for declaration that are module updates at times marked by those little vertical gray ticks that are above the horizontal axis. The rightmost plot superimposes a histogram for the detection statistic in gray with the theoretical densities that our algorithm estimates. The vertical red lines then show the linear scale range of the thresholds for detection that our algorithm estimates to maintain an acceptable constant false alarm on noise rate. The detections that exceed the threshold also correspond to estimates for the source azimuth. And here are those estimates. The stars on the rightmost plot are cataloged sourced azimuths. The polar histograms show the azimuths that our algorithm automatically estimates. The algorithmic azimuths agree with the catalog source azimuths within a couple of degrees for the first 2 explosions. The mismatch then grows for the second 2 detections as the signal overlaps more with preceding waveforms and the SNR degrades, but it still stays within 17 degrees or less, as you see there. So we nailed it. Now that we confirm that we can detect and estimate azimuths for cataloged events, we will quantify the sensitivity of our detector. And so informally, this means we will measure if our detector module triggers often on small explosions or if it often fails to trigger on those same explosions. However, we cannot make these measurements with our present data. Even though Dando et al. Has a bunch of data, the catalog contains signals that by definition we can detect and record. And what we'd like are explosions that are harder to detect. So we therefore make a data set with more explosions that are smaller with an established augmentation process that's been documented since at least Schaff in 2008, if not before. But in summary, this process uses a physical scaling law to shrink waveforms in amplitude and thereby mimic signals sourced by events with a lower yield. Again, using an empirical magnitude to yield scaling relationship and some physical arguments, of course. So in pictures, what we do is we collect seismograms from an explosion. We then scale the seismograms to mimic records sourced by explosions with lower yields. We then add these templates into noisy data at a regular schedule that is marked by those orange lines in the middle and right plot. This turns our data set into a record with one explosion into a record with many smaller explosions. And I should also add that we ensure that we don't inject amplitudes of a given yield into the same time of day every day. We randomly permute that. But then what we do, then what we do is we process this augmented data with our detector module and run it over a single band in Bayesian mode. We then count the number of true positives that we recall versus the size of the explosion source in kilograms of yield. So here the vertical axis shows the percentage of events that we detect out of 100, and the horizontal axis shows the source size. Markers show raw normalized counts. The curve shows their centered moving average. We see that we detect near-surface explosions as small as 110 kilometers about 80% of the time, and explosions as small as 145 kilograms about 95% of the time, each from about 25 kilometers from the source. We also localize the azimuth of the source within roughly 10 degrees. Not bad. So now we compare this single band performance to our module's multi-band performance. The gray curve now shows the mean performance curve of our single band detector. The black curve shows the mean performance curve for our multi-band detector. And because the black curve sits both above and to the left of the gray curve, in other words, it's hugging the vertical axis more, it shows a higher true positive rate. In numbers, this means we now detect explosions as small as 73 kilograms at station AKBB about 80% of the time. This is a 40 kilogram decrease in yield relative to our single band case and presents an increase in sensitivity. This is all at the same constant detection rate. We also maintain about 10 or 12 degrees in error in the source azimuth. This is all, again, at 25 kilometers from the source as recorded at station AKBB. So, what did you hear today? Explosion monitoring, first off, requires a capability to detect signals like RG at local distances with sparse sensor coverage in this particular scenario and others. We provided today a detector that efficiently triggers against airborne cataloged explosions or near-surface explosions and outputs good estimates of their source azimuths from one sensor. That's key. You don't know the azimuths ahead of time. Our impact here is that we are also able to provide a pseudo-empirical estimate of how sensitive our detector is so we can quantify its performance in regular monitoring. Our next steps will be to use detector output from the, source azimuth output from our detector with multiple sensors, shoot rays back, and hopefully estimate source locations. And lastly, I will invite you to get more information from Jonas Kintner on the cross-validation of this detector with a Stockwell transform, which I did not have time to cover today. And I thank you for your time. I provided some possible backup topics for questions if you can't think of one, and I'll take questions now. Thanks a lot.